I'm Frank McSherry. Sort of, you can see up on the slide. I'm going to talk about concretely some work that we did recently on doing machine learning on DryadLINQ, but I think it's a really good demonstration of writing slightly higher level algorithms in DryadLINQ. So we've seen a bunch of examples of little fragments where you might say, I want to count a bunch of records or something, but that isn't what most people necessarily want to do. They don't just want to count things. They actually have a goal in mind, maybe doing some clustering or some classification. We'll see a few examples. And they'll lead into the lab that's going to come up subsequently. We're going to do some linear algebra work and see some stuff. So this is going to be an example both of how to write, and hopefully I'm going to convince you how not complicated it is to write fairly simple algorithms in DryadLINQ, as well as a few cute observations about how to make them perform quickly. So ways that programs that you might have written on a single machine would go slow if not carefully implemented in DryadLINQ. We'll see that there are a few neat tricks to apply and essentially explain to DryadLINQ how it can go quickly and efficiently. Please do stop me as we go along. I'm going to reiterate a few things at the beginning just about DryadLINQ. I mean, it's not a wildly different take than other people, but I definitely like to try to restrict myself to think less about the system and more about the programming language. So instead of wondering how things actually implement, just try to keep myself at the LINQ abstraction and not worry too much about Dryad. So this first half of the talk, I'm not going to say too much about. Just to recap the rough players here, we have LINQ, which is this programming language. It's a way of talking about how to manipulate collections of data, collections of records in .NET, in a way that I assert is nice and data parallel. It exposes the independence of certain parts of your computation. It explains that certain records can be computed on without needing to interact with other records in the data set, and that's going to let us execute things efficiently. Dryad, as we've talked about, is this distributed execution environment. It's a clever system that goes and implements things fairly efficiently, reliably. And DryadLINQ then is this essentially compiler that takes these LINQ expressions and maps them down to Dryad computations, which then execute in a highly scalable, reliable manner. What I'm going to spend a little bit more of the time talking about after I review some important points from the first few things are some examples from some of my programming in DryadLINQ to some fairly simple machine learning tasks, so some clustering tasks. K-means is a clustering task. Decision tree induction is a classification task. And then the lab is going to be linear algebra and playing with the singular value decomposition. I'll try to say a little bit about that to get everyone started and excited and all of that. But then a lot of the lab is actually going to be building up sort of in an analogy to what we did in the first two steps there. There are a lot of other applications that we've put together. So these aren't the only three that we could possibly think of. There's a lot of stuff out there. As we'll see, the main restriction on these applications tends to be what tasks can I actually figure out how to describe in a data parallel manner. I need to be able to convince DryadLINQ that my computation is actually properly data parallel, that it's a nice collection of LINQ statements that expose the parallelism and don't simply dump all of the data back onto my local computer and work with it there. All right, so LINQ, we've talked about before. You want to introduce, this is, essentially you should just think about it as operating on collections of data. And I want you to think about this very abstractly. Don't think about arrays or particular implementations thereof. It's a collection of data that someone else is going to manage for you. You get to interact with it indirectly through these operations like select and where and group by. But really, you're only asking someone else to perform these operations for you. And that's really the power that we're trying to get out of this, is that the cluster, which is big and powerful and has lots of resources, is capable of responding to these requests for selecting, transforming records, filtering records, those sorts of things. And by giving it responsibility, therefore, your computer, the sort of poor single little laptop that you have or something, it isn't actually going to be burdened with doing all this computation. So we really want to think about how do we take the computations we want to do and turn them into requests, essentially, that we can hand off to this LINQ provider, be it the cluster or whatever. Importantly, these operations are functional and declarative. So declarative meaning I say what I want to do. I don't actually do it myself. I let someone else do it. And they're functional in the sense that they're not mutating the data underneath. We're describing how to produce new data sets. It's an important part of a lot of what makes this computation efficient, that we're not actually changing underlying data sets where we're just producing new results, new aggregates, and stuff like that. And again, the main point here is that LINQ is going to allow the data provider, the person holding the data set, to figure out how to respond to all of these questions. If the data lives on your own local machine, it executes on your local machine. And if it lives somewhere else, it is in charge of figuring out an efficient way to execute. And Michael has described, for example, how it might actually go and execute. But again, we're not going to worry too much about how it actually does execute so much as trying to push as much of the computation to the LINQ provider as possible. So let's look at a real simple example, the k-means clustering problem. How many people here are familiar with k-means? Hopefully not everyone, because I was going to explain it. Good, OK. So k-means is an iterative clustering rule that is fairly simple. So think about a data set initially that's points in space, just three-dimensional points in space, lots of them, though, so millions or billions of them. What the k-means update rule does is it takes a set k of candidate cluster centers. So again, just points in space, but a very small number of them. And it partitions up our millions of points into k parts, one for each of these centers. And each part contains those points of our millions that are closer to this center than to any other center. Right? So if we had 2 points, for example, here and here, then space would be partitioned in half, and everyone on the corresponding side of this line dividing the two would be associated with the respective center. The centers are then updated by the average of all of those points that were associated with each of these centers. So this process iterates. So we improve the centers. They accumulate some points and then are updated to the average. And then we repeat the process. And eventually it stabilizes. So I'm going to describe this to you now using just a few lines of LINQ, which I will assert is correct. And we'll try to convince you that it's correct. And then we'll spend a little bit more time developing how it would actually work on DryadLINQ. So I'm going to imagine that someone, me, has already written this method called nearest center, which takes a vector as input, some point in space, and a list of candidate centers, these sort of k centers. And it tells us which of these k is nearest to this point. And this is what's going to tell us which center it should be associated with when we do this updating. But then, with access to this nearest center method, we can describe our update rule fairly simply. So we imagine a collection of vectors. These are the points in space. Some collection of this vector type that, again, we want to think of as being very large, millions or beyond, potentially unbounded. And then we have another list. I'm also going to have this be one of these LINQ objects, but it's going to be very small. It could be an array if you wanted on your local computer, maybe 10 or 20 or who knows how many centers. And as I described the algorithm, we took all of the points in space and we associated each point with a center and averaged everyone by the center with which they were associated. That's really not terribly complicated in LINQ. It's just a group by first. So we say take every point and figure out which center it's closest to and produce a group, one for each of these centers of those points for which the nearest center is a particular center. So this group by will result in, again, just a collection of lists, one for each center, of those points that feel that they should be associated with that center. And each group then is transformed using this averaging. And I had to write average out not as average because these are vectors, points in space. And so we actually need to write out a summation and then divide by a count because the dot average method just applies to doubles and integers and stuff like that, not high dimensional vectors. But all that we're doing here is just averaging each of the points in the collection. So these two steps, taking our vectors, grouping them by which center they find themselves nearest to, and then averaging each of the groups results in a small list now of just as many records as there were centers in the first place, which are the next iterate, essentially, of the centers associated with k-means. So that's an algorithm. I don't want to claim that k-means is a very advanced, complicated clustering thing, but it's certainly popular. People use it a lot, in part because of its simplicity. And it's really quite easy to write in LINQ. That's all we've done so far is write it in LINQ, not DryadLINQ yet. So let's develop that a little bit. I guess what I want to convince you of now is that we can iterate this a little bit too. So I described how to do one update step, and I'm now just going to stitch together a few of them. we wrote this on the previous slide. This is how to do one step of k-means. So we're still just in LINQ at the moment. One step of k-means. And one thing to look at here is the type that I returned, that the new centers have, the updated centers, is still one of these iQueryable types. It's one of these LINQ data sources containing a small list of vectors, which is exactly the same type as what we fed it as input. So we can actually feed them back into this algorithm and just continue, essentially stitch together as many iterations of these as we'd like. And I've written the code here just as a for loop, mostly to try to convince you that this is pretty close to the code you would have written if you were running on your own local machine anyhow, right? A little for loop that says for each iteration, run through and set my centers object to be one step using my k-means update rule. And this works just as well for LINQ. The only difference is that the centers thing isn't actually living on your computer being updated as we compute. It's essentially a handle off to wherever the LINQ data source is. Maybe that's on the cluster. Who knows? And a description of how we would like it computed. So when we look at the end result of this, maybe after we did 10 iterations or so, there'll be a big, long description of how centers got computed. It was the result of, sneak back a slide. It was the result of first taking some vectors, grouping by the stuff, then averaging them, then feeding that into another grouping, and then averaging, and so on and so on and so on. None of this actually executes, though, yet, until we do something with the result. So the intention of this was to show you that the programs that you write are not especially different than what you would have written if you had an array sitting in front of you and you're actually going to go and walk through it. We've just abstracted away the responsibility for managing each of these data sets. So our local computer isn't in charge of doing the group by and the averaging. Someone else is, but we've still described how the computation unfolds on our local computer. All right. Going to DryadLINQ, you guys have seen these before. DryadLINQ simply is a Dryad implementation of LINQ. It's just like LINQ, except you have a big cluster sitting behind each of these data sets, and a smart way of mapping each of these data parallel computations, these group bys and the selects and what have you, onto this cluster and onto partitioned data sets. So it's exactly the same data model in the sense that what you see in front of you is this LINQ iQueryable type, which is this big collection of vectors or whatever it is, and you interact with it in exactly the same way as if the data were local. You say where and select and group by and all that stuff, but someone else does all the processing for you. This is great because it goes really fast on lots of machines and handles very large data sets. We're also going to see a few cute optimizations that it does for you along the way. Now, in principle, these could have happened on your local machine, but typically on your local machine, data are small enough that investing a lot of effort into introducing optimizations is not high on their priorities. It is high on our priorities because when you're working with a terabyte of data, speeding things up by a factor of 10 is important. So we've seen a little bit about how to do this before, how to map these operations onto these DAGs that Michael has talked about. It's important to bear these in mind when we think about how our program is being written, though. When we go and apply a group by method, that's going to cause something different to happen than invoking a select or a where will. And we want to pay a little bit of attention as we start to analyze our program and think about how it's going to perform, of what methods we invoked and what they cause to happen to the data underneath. If we run around and do group bys all over the place, we're going to shuffle a lot of data around over and over and over again. And we should be mindful of that. Whereas things like select and where are relatively cheap. They don't involve sending the data around, and they can usually be pipelined with other operations. That is attached, for example, right before the group by, we can just filter the data if we've asked it to be filtered as we're reading it off of disk and without actually shuffling any data around. All right. So hopefully you guys have sort of intuited this already, but one of the really neat things about DryadLINQ is that the program that you write is essentially, with a few very minor modifications, essentially the exact same program you would have written if you had the data locally on your own computer. And that's really good. It means you don't have to change the algorithm at all or the implementation even to start using DryadLINQ. You can just connect a different data source to the same algorithm, and the hopefully exact same algorithm will execute, though somewhere else and more efficiently. The only difference is going to be that these inputs that we supply to the algorithm the initial vectors and centers things need to be no longer in-memory arrays on your laptop or whatnot, but handles to data sources on the DryadLINQ cluster. And as soon as you do that, the cluster starts handling requests for where and select and group by and everything like that. And magically, everything starts to work. Now, it's glossing over a lot of stuff, and you'll discover as you start playing around with DryadLINQ in the coming hour or so that it's not quite as simple as that. And there are some interesting things that crop up in terms of performance. And we'll sort of point out a few of these and try to avoid tripping ourselves up too much. So what's an example? So if we really did have a terabyte of data for k-means, and we really did have a very small number of centers, let's say we only had 3 centers for k-means, the group by is going to try to take our terabyte of data and break it into 3 parts. Right? We've asked it to associate every record in that terabyte with one of the centers in our data set. So at least one of these centers is going to get 1/3 of a terabyte associated with it. And as Michael described, if we don't think too hard about this, it's going to dump that 1/3 of a terabyte on a single machine and ask it, please load all of this up and take its average or something like that. And that's just not going to work out properly. The poor machine is going to get overloaded and probably crash or stall or something like this. So Michael described a little bit about this eager pre-aggregation that goes on. In the case of count, for example, DryadLINQ was capable of being smart and saying, I know how count works. Count is associative in that I can pre-count before I start shipping data around a lot of, essentially all of the groups, and then sum the groups instead of actually shipping the whole collection of records over and actually counting them. DryadLINQ, fortunately, is relatively clever and is actually capable of doing more general reasoning than this. So let me just flip back to the implementation here. What we wanted to do with these groups once we distributed them was average them. Now, averaging isn't technically, let's say, associative, right? It's if I have a big data set and I average approximately 1/3 of it and approximately another 1/3 of it, I shouldn't just take the average. That's not technically correct. If it were exactly 1/3, great, but it's not exactly right. However, it turns out DryadLINQ is going to be smart and appropriately annotated. It will realize that this aggregation is associative and that this count is associative, and it will rewrite the query to be a pair of associative queries, the summation and the count, that it does manage sort of associatively, pre-aggregates both of these quantities, hands both of these quantities, passes both of these quantities around instead of all of the records, and once they're finally correctly computed, then does the division and gives you the correct average, having moved only a very minimal amount of data around. So that's very nice. We didn't have to do anything to make this happen except annotate the vector plus operation as associative. So when I wrote the vector class, which I didn't show you, there is an operator plus associated with it, which tells you how to add 2 vectors. And I put a little tag in front of it saying associative. And DryadLINQ was able to figure out from that point on that it could magically rewrite this averaging to be very efficient. And I'll show you how efficient in the next slide. The second thing is possibly a little subtle. I reused this variable centers every single time I computed the key associated with a vector. Right? I said, look at the collection of centers and find the center that you're nearest to. And if you actually run this on your laptop instead of using DryadLINQ, this is going to behave hilariously. It's actually super exponential in the number of iterations. It's really bad. And the problem is that it recomputes centers every time you need to use it. Now, because everything is assumed functional in DryadLINQ, and DryadLINQ is clever, it will compute centers only once and distribute it only once to each of the parts, as opposed to computing it for each possible record that might be interested in using it, of which there are millions or billions or so. So DryadLINQ is also good at caching data that's reused. This is another really nice property that it has, and that saves us a bunch of headache. No joke, there are also a lot of other optimizations going on in here that I've probably forgotten about because I've been using them for so long. A lot of very pleasant things that you start to use the system and you get a feel for what stuff is DryadLINQ basically trustworthy. You can just ask it to go and do this, and it will do the right plan for you and figure out all of the correct ways to do things that you had sort of forgotten that a naive implementation of something like this wouldn't have done. Let me show you a picture that describes a little bit about how this algorithm. Yes.
What happens to this line?
So the intent here is that if we did this group by, and this is the case where we have maybe 3 centers, we do the group by on our terabyte of data, and if we actually do try to shuffle all of the records around, the whole terabyte of data, we're going to try to co-locate all of the records associated with one key. And if we send a third of a terabyte or more to a single machine and make it responsible for the computation now that follows the averaging, we've got huge data skew. Even if it runs, which it probably won't run, we've horribly misused our cluster resources. Only 3 machines are actually going to be doing any processing where we might have hundreds of them. Right, so the problem is that the group by as written is sort of oversimplified in asking you to co-locate the data first and then compute on it. And by virtue of DryadLINQ being clever, we can still write the program that way, even if it executes slightly differently, by first computing the local sums and counts and distributing those, co-locating only the partial sums and counts of the vectors. One thing that we could have done actually for the lab that might have been interesting is have the same programs both for LINQ, local LINQ, and for DryadLINQ, and watch the local LINQ things take an enormous amount of time and behave very badly. There's some naughty things that normal LINQ does because it assumes you're working on very small data sets that DryadLINQ fixes in some sense. We'll see a few more examples as we go along. So if this wasn't the most compelling one for you, it turns out it is in some sense technically very compelling, and that your program wouldn't work without it, which is sort of nice. On the other hand, maybe you don't care a lot about k-means, so we'll see. This is a very helpful optimization that DryadLINQ does, though. It makes a lot of very expensive jobs a lot more efficient. Yeah?
Yeah, so the way you written the query, nearest neighbor is like
Yes.
Wouldn't that be a query by itself?
Wouldn't it be a query by itself? Yes and no. So you could certainly try to write that as a query if you want. DryadLINQ doesn't respond especially well to nested subqueries. What it will actually try to do is try to fire up more Dryad jobs for each of these nested, and you really don't want to do. You don't want your billions of records firing off billions of DryadLINQ queries. So you're right. Conceptually, we do actually write a lot of code in LINQ for these UDFs, the user-defined functions, but we don't actually use DryadLINQ to execute them. So this is a picture describing the DAG that the k-means computation produces, and some information about the amount of data that gets transferred around, or sorry, the amount of data that exists, and we'll see in the stages that actually do data transfer how much gets moved around, and hopefully we'll convince you that it's relatively small. So this is the k-means algorithm. This is 2 iterations that we've seen. We have a data set over here of vectors, and this is initially 100 gigabytes large. This is just what we were playing with. And some set of initial centers, and it's 350 bytes. I don't remember. I think that maybe 10 centers, something small. So if we actually did a big data exchange and moved the 100 gigabytes all around on the network, this would be annoyingly expensive, a lot of wasted network bandwidth. Instead, we'll do this pre-aggregation where we compute the local to each of these parts, sums and counts, and only pass those around. So this first step here, each of these parts is going to compute. Well, first they'll associate each record with a center, of course, do locally a grouping by the centers, figure out, for this part at least, what is the sum and what is the count, and then they'll exchange all of this information. They'll send their partial sums and partial counts around in such a way that each group receives, in this case 3, I guess, incoming batches of information about partial sums and partial counts that it can reassemble into the correct answer. But the amount of data that's sent around here is very small, 24K. So it's quite compact. Certainly compared to 100 gigabytes, this is essentially free. It's essentially nothing. A little bit more work needs to happen now. Once they receive these partial sums, they need to actually be assembled, put back together into one big pile. We're putting together the centers vector again, and we need the full center from each of the folks who are aggregating the centers. And then it gets redistributed, and we repeat. So we take the initial the new centers and do exactly what we did in the first half of the computation. We locally group all of the vectors. We never end up actually moving these 100 gigabytes around. They stay on disk, and the only data that gets transferred around to the network is this 24K-ish amount and the 350 bytes of the centers that get shuffled around. So it turns out this ends up as a very, very efficient computation from a network traffic point of view. Sorry, yes? So I'm not entirely sure I understood the question. Let me answer a possibly related question and tell me if this. You could rephrase it. Yes. Well, how about you rephrase it, and I may still answer a different question. But. So for example, centers being a query, right? Centers, when we end up feeding it back in on itself, it's a query that DryadLINQ is in charge of managing. Right? It hasn't been executed yet, but it's still a handle to a query that DryadLINQ is in charge of executing. And
so instead of that, say instead of the nearest center, or the nearest center itself has 3 different functions or queries inside it. Will those 3 be operated individually or as a group, as an entire function?
So what DryadLINQ will do when it sees something like this in your code, so it gets a chance to look at the computation before it actually executes it. It will look at these methods inside and try to resolve them. Right? It will say, I know what nearest centers is. Let me write that down. I know what vector is. That's going to be supplied as an argument. I don't need to worry. Centers. Oh, centers is this DryadLINQ query that I have. I know that I'm in charge of executing that already. So I will make sure that it's available for me when it comes time to actually execute this. So it's going to be executed as part of the same DryadLINQ query using the rich parallelism and stuff like that in DryadLINQ. Yes, and such. There may be other things in there that it doesn't exactly know. They're not DryadLINQ, things maybe like a SQL query or something crazy like that. And it will attempt to resolve them. It'll say, great, let me actually force the evaluation of this so that I can figure out what this quantity is to be able to run my query. But it's very good about delaying the evaluation of things, DryadLINQ queries, that it knows it's going to be able to evaluate during the run of the query. So I don't know if that actually answered the question properly. OK, great. It's usually very good. It doesn't always do that. And in cases that it doesn't do that, we try to contact Yuan and ask him to make it do that. So this is k-means. Hopefully, the intent of showing you k-means was to try to convince you that they're fairly simple to write programs, possibly just in terms of number of characters at least, that produce fairly efficient, highly efficient, in this case, execution plans. That this scales essentially arbitrarily. If we took this up from 3 to, it actually ran on 200 odd machines. And the amount of data being passed around is essentially negligible. So we can crank this up to terabytes if we wanted to. The only thing that slows down is that we do need to do a bunch of computation locally doing these local groupings, and it does eventually take time. But the scalability question isn't a big deal. We can add more machines and run across a bigger cluster at essentially no cost. So the second example I want to give, and what I really want to do actually is check what time it is. Excellent. Is about decision tree induction. So if there are questions about k-means, this would be a great time to ask them, or about things that I've said that you don't believe, or anything like that. I'm going to slide into a slightly different example that calls out a few different points about writing programs in DryadLINQ. All right. So let me say a little bit about what decision trees are to sort of motivate what we're going to be computing and why we might be interested. So decision tree is a classifier. And for the purposes of the next few slides, at least, we're going to think of it as a complete binary tree down to depth d, or something like this. And each node in the tree contains the name of an attribute. So it might be, the first node in the tree says gender. And the idea is that the setting of the binary attribute gender for each record determines which direction down the tree it should be filtered. So the tree is essentially going to filter records down the tree by looking at their attributes, and based on the binary values in the attributes, tell it which way to travel down the tree, and eventually it will arrive at a leaf, and the leaf will hopefully tell us something about the record in question. So it might be, for example, trying to diagnose the incidence of some disease in a person, and we might be looking first at their gender, and then if they're male, whether they're over 6 feet, and if they're female, whether they're over 5 feet. So we've described now sort of a single node and then 2 sub nodes, and so on. It goes down, and your responses to the questions that you've encountered determine what questions you get asked next. So a natural question is, how do you build a good decision tree? If someone gives you a big pile of data that has a bunch of records with binary attributes and binary labels associated with them too, so data to train on, how would you learn or induce a good decision tree? One fairly common way is to take a partial tree at the moment. So let's imagine you have a complete tree down to depth I, and you want to produce the next layer at I plus 1. Take the tree, filter all the records down to their corresponding leaves at depth I, using the existing tree structure. And at each of the leaves, take the records present and pick the attribute that optimizes the conditional entropy, essentially, of the label. So try to pick an attribute that filters all of the positive examples in one direction, all the negative examples in a different direction. And it turns out conditional entropy is a good way of doing this. If you don't know what conditional entropy is, don't worry. I forgot its definition too, so I didn't put it on the slide. But fundamentally, it's a way of quantifying how good a job did we do of splitting our essentially initially mixed population with multiple different labels into 2 sets that are hopefully as coherent as possible in each of the subsets. Each attribute will induce a certain conditional entropy. Some would be very good at splitting the data into positive and negative examples. Some will be bad. We want to pick the ones that are good. All right. So that's the spirit. Let me describe a really easy way you could write this in LINQ, and then we'll see that it doesn't work, and it's not going to work. So here's one way of trying to code this up in LINQ. It's relatively simple in spirit. So we're just going to we're going to define this record class that has a label, and it has an array, a Boolean array of attributes. So each attribute of which there might be, I, let's say, have a setting, true or false. There's a little routine here, which I don't want you to worry about too much, which is how you filter a record down the tree. It basically walks down the tree looking at the appropriate attributes and updating the node that the record is currently at appropriately, and then looking at the next attribute it should look at, and so on. So think of it just as a function that takes records, a partial tree, and returns the name of the node that the record filters down to. Then one way to write what we want to do is say, well, we're going to filter everyone down to their current leaf in the partial tree. Let's do that. That's a big group by. The key is an interesting function here. We could have written it if we wanted it as a recursive function. I wrote it as a while loop instead, but it could certainly be more complicated. But it's an interesting function that processes the record and the partial tree so far and tells you what node should you be at. Once we've done this, we take each of the records, each of the sets of records at these leaves, these groups, and there's just some method, that a user-defined function I've written called findBestAttribute that flips through all of these and tries to figure out which attribute optimizes the conditional entropy. So it turns out this doesn't work out for exactly the same reason that I might have initially scared you that k-means wouldn't have worked out, that it co-locates too much data at individual nodes. So for example, at the very first level of the tree, everyone is at exactly the same node, and we're actually going to go and force all of the records to be sent to this one node. This findBestAttribute method is not associative or anything funny like that. There's no smart way for DryadLINQ to decompose it for us automatically. So even though this is a fairly simple description of what we wanted to do, this isn't actually going to result in a good DryadLINQ program. Which is too bad. It would have been a wonderful example if it did just work out perfectly. But the intent here is that occasionally we do need to take an algorithm and rethink a little bit. Why is it that this is really data parallel? I mean, this is not a good description of why it's data parallel. This says put all the records together and then think really hard about it. And that's not a good description of parallelism. So we're going to tweak things a little bit. We're going to use a little bit of knowledge about the problem domain And this is an example of hopefully what you guys may end up doing with your problem domains, is taking a little bit of knowledge about what do I really need to compute the quantity of interest and exploiting that. So, in fact, when we did this update of each of these nodes, when we picked the optimal attribute with respect to the conditional entropy, it didn't actually need to look at all of the records. It needed to look at something related to all of the records, but actually fairly much simpler. It only needed counts of each of these pairs of value and label. So for each attribute that might exist, it wants to know how many records in there had the attribute set to true and the label set to false, and how many had the attribute set to true and the label set to true. The 4 combinations of the attribute value and the label of the record induce 4 counts for each attribute. And if you gave this information to the find best attribute subroutine, it would still be able to go and optimize the conditional entropy. That's enough information for it to run its computation. So we're just going to tweak our program a little bit. We're going to rewrite it so that instead of grouping all the records together, it first does this big data reduction. So it's going to take all of our records and produce. It's actually a little interesting. It's first going to explode the data out. So it's going to take our records, which are a list of attributes, and for every record, we're going to produce a list of. We're going to produce a number of elements equal to the number of attributes that it has, where we list out what node does it currently filter to, what attribute are we talking about, what is the value of the attribute, and what is the label of the record in question. So if we had 10 attributes for each record, this is going to produce 10 records for every initial record, but we're then going to hit them with this group by and count, right, which is going to do this massive data reduction that we saw both in the histogram example with Michael and also in the k-means example with the averaging. Right, so although the data does get quite large here, we never actually send this data anywhere. Right, it locally on each machine expands, but never actually makes it to disk. It gets collapsed before it's ever really needed. Here is an example. This is the same picture that we saw for k-means before. We're seeing here the performance of this decision tree computation with data sizes present. So we start with a much smaller data set, this 12 gigabyte data set, because I think in this case they had about 50 attributes or something like that. So the explosion of data that went on actually means that the amount of data that we're processing is in the hundreds to sort of terabytes, hundreds of gigabytes to terabytes of data. It's just never actually transferred across the network. So within this blue node, there's a substantial amount of data that's created and then consumed again, and a very, very, very small amount of data, 500 kilobytes, that are actually transferred across the network. These are these aggregate counts that get shuttled around to help define the conditional entropy. It turns out that the rest of the computation is actually also data parallel. Not only once we get these counts and shuffle them around, we end up doing a few more group bys. The sort of find best attribute actually has group bys in it and stuff like that. So a few more steps go on that do further data reduction until we end up with just 16 bytes describing the attributes. Essentially, each node has a single bit associated with it, which is, has an int associated with it, which is what is the index of the attribute that I would like to have as my attribute that I'll use to classify people next. And again, you can stack these folks as we did for k-means. This can then feed back into the next round. As the iterations proceed in the decision tree, actually we shuttle around more and more data. So as the tree gets deeper and deeper, the number of aggregates we have to move around increases. Right? Remember, we had aggregates for distinct values of these quadruples, and as the number of distinct nodes increases, we might have more and more aggregates floating around. But the number of nodes increases by a factor of 2 each iteration, and we can get quite deep in the decision tree before the size of the intermediary aggregates actually becomes something that we have to start worrying about. Alrighty, I have some stuff that I'm hesitant to go into about the linear algebra stuff. Let me pause here for questions about stuff you guys have seen so far. Anything at all? Is it at all plausible that you guys would feel comfortable writing fairly simple algorithms in something like LINQ, and then imagining you would understand how they might execute in DryadLINQ. This is going to be the subject of the next lab. It's going to be eased into very gently as we go into it. But hey, hooray! Thank you. If people are totally not clear on what's going on, I'm more than happy to go through things again a little slower, something like that. The next, let's see if I don't want to show you that slide, unfortunately. There's an answer to one of the questions on that slide. So we have a bunch of printouts for what the lab is going to be, and I want to roughly describe what it is so that you get a sense for it. And then there's also description in each of these write-ups. They're beautifully written, I'll have you know. Apparently about 6 pages long. So the idea is to build up, starting from almost scratch, some linear algebra tools, so matrices and stuff like that. And some code has been provided that starts you out by defining an entry class, so an entry in a matrix, which is a record that has a row and a column and a value associated with it. And we're going to think of matrices as being these collections of these triples, rows, columns, values. And we're going to start writing some fairly basic linear algebra operations, stuff like addition and multiplication, transposes, stuff like that, all of which can be very succinctly and also relatively efficiently written as LINQ expressions. And so we're going to do that. That's going to be the first stage of the project. It's sort of broken into 3 parts, 3 stages. But this is the first one. Playing around with this, seeing how these addition and multiplication operations end up running on DryadLINQ. They'll start out hopefully very bad, not because I wish ill on any of you, but hopefully there'll be something to learn. You'll implement them naively at first and then realize, aha, there's something clever I could have done. And it's sort of designed to try to tease that out from you. The second thing we're going to do, once we have addition and multiplication in place, is to try to build up an algorithm. So we're going to look at programming a very simple algorithm that computes the singular value decomposition of a matrix. So anyone familiar with that, excellent. It turns out this is also very simple to describe in DryadLINQ, or at least very concise to describe in DryadLINQ. And whether you decide that it's simple or not is a different matter. But we'll have you put that together. It turns out it's very simply described as a bunch of matrix multiplications, essentially. And that will be a bit more complicated. So it's not just as simple as additions and multiplications. You actually have an algorithm now that's supposed to produce correct outputs and stuff like that. So there'll be a little bit more testing and execution and seeing, have I really structured my program correctly? And then the third hunk is essentially performance optimizations. And depending on how comfortable people feel as they're going along, we can either get that far or not get that far. There's certainly interesting things to learn about optimizing the performance, but if you're still having lots of fun figuring out how to write these algorithms in the first place, that's great too. But this particular example of matrix algebra and the SVD teases out a lot of really interesting performance optimizations having to do with where do I put my data so that I don't have to constantly shuffle it around, and how can I write my query slightly differently so that, for example, I don't have to constantly talk back and forth between my computer and the cluster, these types of things. And hopefully, we'll actually get everyone to the point that they have a running version of the SVD and you feel empowered about writing things for DryadLINQ and are very excited about going forward into the next day with doing something similar of your own choosing. But, yes? Decision trees, yes, okay, great.
So, can these be used in, say, real-time?
Absolutely not. Sorry, the question was, can they be used in a real-time anything? Yeah, and the answer, no matter what that was followed with, the answer is no. Sorry, that's a very good point. Yeah, so this is more about taking a large collection of training data, thinking hard, and coming up with a decision tree that absolutely, one of the nice properties of decision trees is it's very fast to evaluate them once you have one already trained. So you can certainly take the output of this data set, appropriate it, and put that in an application that's much more performance sensitive. But the training of it in the first place is something that you'd absolutely love to do on enormous amounts of data, even if the ultimate decision tree that results is not so large that you really need a cluster to work with it.
So after the initial levels of training, how would it be applicable for your time? Like say, the training here is basically continuous process, right? It doesn't like your process 500 gigs of data doesn't mean your decision tree is completely ready. Another probably 100 records would change the results of the decision.
So it's very possible. So the question was, is this, you sort of said, but I don't think it's correct, that this particular training is not a continuous process. So as more records arrive, this computation is defined with respect to a fixed set of inputs, and it runs possibly to completion depending on whether you let it or not. But as more data arrives, DryadLINQ doesn't magically integrate them and go and reevaluate stuff. So as we proceed through the loops of this decision tree, if we did add more data earlier on, it would invalidate previous results. We'd have to essentially throw everything away and re-execute, which is fine. That might be a good thing to do if the new data that you have is important. But it's not something that's automatically going to be done for you. You're more than welcome to Control-C, kill it, go back and restart the job with the new data, but it's going to be something that is done by a higher level than DryadLINQ. How do you handle overfitting in decision trees? So questions, let's see the right way to answer this. It's a good question, except it's not going to be a DryadLINQ sort of question. I mean, we're not going to burden DryadLINQ with the responsibility of a poorly fit decision tree, something like that. So there are techniques for correcting overfitting in decision trees. So the C4.5 stuff goes back and trims parts of the decision tree that look like they might be spurious. They're not sufficiently supported things, and you could certainly code that into DryadLINQ also, something that will do a final post-processing pass over the tree and look for, use these statistics to look for support and clean them up. But that would be, so this is essentially a faithful implementation of the ID3 decision tree implementation, and there are more advanced ones that would require more advanced corresponding DryadLINQ implementations, but certainly DryadLINQ is not taking responsibility for anything like overfitting or quality of fit, or whether you have a bug in your decision tree implementation. It's going to implement it for you and run the code that you told it to run. And hopefully, like for example, if your conditional entropy function is wrong, which mine was at first, it's going to run great. It'll produce something for you, and it's not going to be correct. But DryadLINQ isn't in charge of detecting that sort of error. Yeah. Excellent. All right. So what I think would be a good idea, I need to supply people with lots of information before you wander off to your next programming task, in the form of these sorts of pieces of paper and where to look on the computers that you're using for the project file associated with the matrix stuff. There was a URL that was on your slide.
The place where the samples were before the cancer robot, there's now an additional directory called DryadLINQ, which is where you can look for things with this paper. It's not there, that's because I failed to copy it to one of the computers.
And you should tell us.
Tell us and we'll get it there. And if you attempt to run it, you will find those errors, and that is correct.
Yes.
You have to do some work before you do it.
So when you open up the project, intentionally or interactively, you start reading through it, and it gives you instructions on what you might be doing with the code. And one of the first things that you're going to have to do is start to fill in some blanks that are currently making the code a little bit unhappy because it's not returning anything from the addition or multiply functions. But once you get those in place, things should start to run just fine. There are, for each of these sections, answer keys in the code. They're commented out and collapsed, so they don't start being visible to you, though if you want to go and look at them, you're entitled to, but it's going to possibly make it a less interesting experience. We don't want you to sit there and hit your head against something that doesn't make a lot of sense for a very long time. So I was sort of thinking there are 3 stages and 3 rough questions in each of them, and I imagine once you get up and rolling with the project, there'll be some setup time, but if it's sort of 10 minutes-ish each, if after that point you're like, I don't really know where this is going, maybe go ahead and look at what the answers are saying about the way to go and do a particular computation. There might be something that you've missed, or if nothing else, you'll learn when you see the answers. Like, oh, that's interesting. Maybe I didn't think of it that way, or who would be so insane to do it that way? And actually works out. So what would be good is if I don't think there are enough of these for each person to have one. There 2 per group is roughly the number that you get. even 3 is something, is too much? No, is okay. Is doable. So we want to make sure that each group gets at least one of these. I will leave them on the table and you can figure it out. But if you're in a group that doesn't end up getting one, what you should do is look around for another group that looks really smug and take one from them, something like that. But then you should be able to head back to the computer, sort of sit down, open up the project file, the DryadML project file, and things should start to come together in terms of problems to solve and stuff like that. Are there questions about that? We'll certainly be circulating upstairs, able to answer questions, help you guys work through, hopefully, some things. There's a few things that may be new as you go along that we haven't belabored extensively in here. One particular one that you may end up needing just to check on the answer G4 is the implementation of multiplication uses join, and we didn't spend any time really talking about the syntax of join. One of the things that's going to be very nice when you start playing with these things in Developer Studio, which I highly recommend, is the Intellisense aspect of Developer Studio, which is essentially hand-holding that the Developer Studio does in terms of writing these programs. So if you have a data set, your vectors data set, you type dot because you want to type a method. It'll give you a drop-down of all of the methods that this object supports, and you can go down to join, for example, and it will tell you the signature for join. What functions does it expect to be supplied to get join up and working, and hopefully some of these things will be pretty clear. Though if you do get stuck, especially on multiply, that's something that's a little complicated, but it's only one line, so I couldn't really write half of the line for you. Don't feel bad about cracking open the answer key and just saying, okay, that's ridiculous. Let me just put that in my code and be done with it. Alrighty. Oh, thank you.